now recording. It should be recording right now. Okay, that's good. All right, so welcome to the third tutorial. All right, so we'll just go over some of the number things, and if you have any more questions at the end, we can talk about them as well. Okay, so just a very brief review of how to find numbers, right? So generally, it's the max formula that you're looking for, right? So if you have so the main idea for nimbers, you have a game G, and you have the options. Let's say H1 to HK, and suppose you know that each of HI is equivalent to some NI, right? For some nim game, okay. Then you can say that star G is equivalent to the star of the max of these numbers, right? So N1 to K. And so that is supposed to be the main idea for finding numbers. To find the number of a game, you would need to look at all of its options, look at their numbers, and then find the max, which is the smallest excluded number. So it is the smallest number, smallest non-negative integer that is not in the set, right? So max of a number is the smallest non-negative integer not in the set. Okay. All right. Okay. So so that is how you would find the numbers of an arbitrary game. Right. So let's start with the example from class. Somebody asked for the subtraction game. So we will look at the subtraction game. So in the subtraction game, you have a bunch of chips, and you are in your turn, you're supposed to remove 1, 2, or 3 chips, and you would the last person to the first person to have no moves will lose. Okay, so the way you do this is to say, well, you start with the first one, which is the game with no chips. So this one will be star 0. So there are no options. So this has star 0. If you have 1 chip, then you have 1 option, which is move to 0, which is star 0. Okay, so then the max of 0 is just 1. So that's why this is star 1. Okay. All right, and for 2, there are 2 options here. You either move to 0 or 1. So 0 is equivalent to star 0, and 1 is equivalent to star 1. So you're looking at the max of 0 and 1. Smallest number that is not in this list, that would be 2. And from 3 on, everything will just go 3 before that. Okay, so from 3, there you go. From 3, you have 3 options. So everything will have 3 options. In this case, in the case of 3, it's moved to 0, 1, or 2, and you're looking at the max of 0, 1, or 2, which is 3. Okay, and then you just do this repeatedly for future options. Right? So when you have n and greater than 3, the options are n minus 1, n minus 2, n minus 3. Okay. All right. So you're looking at the max of their numbers. Okay. All right. But this is where you say, well, you're just looking at the previous three numbers and taking the smallest excluded number out of it. So for 3, you're looking at 0, 1, 2. For 4, you're looking at 1, 2, 3. For 5, you're looking at 2, 3, 1. For 6, you're looking at 3, 0, 1. And then you're looking at 0, 1, 2 again. So this pattern will just repeat constantly. So every fourth one is going to repeat, right? So this pattern repeats. So that's why you would say something like, we can use induction. And this does feel like an induction, right? Because this is a recursive thing, right? So you are looking at the previous 3 terms. You're looking at the previous 3 terms, taking the max of those. So this repeats every 4 terms. Okay, so you can use induction to get the pattern down. Right, so what did we say about this one? The number is, I guess I can say the number of n is either 0, 1, 2, 3, 0 if n is 0 mod 4, and 1 if it's 1 mod 4, 2 mod 4, and 3 mod 4. And so we can see this visually, see that this pattern repeats itself, and we can try to generalize this using induction to say that this is what happens. Okay. All right. Okay. So, so if you want to find a find the winning move in such a game, so winning move. So a winning game will have has a positive number. Okay, so winning game has a positive number. For example, all these are winning games. Okay, it's just when it's 0, it's not a winning game. Okay. If it has a positive number, that means that when you're taking the max, one of the numbers has to be 0, right? So one option must be equivalent to start 0. Right? So one option must be equivalent to start 0. Right? Otherwise, you don't have a positive number. So this is coming from the max function. And so you have a max function. You have a positive number for your gain. So that means that one of the options must be equivalent to start 0. So winning move would be is moving to this option. Okay. All right. Okay, so that's in this case, in our subtraction game, it is fairly easy to see the pattern. It's not the case in general, so so that's why it is kind of a difficult problem in general. All right. Okay. All right, so this is just a rehash of the things from class. Do you have any questions so far? All right. Okay. So I've also been asked to just talk about a different game. So a game that you have not seen before. So let's do that. Can't draw a line. There we go. All right. So let's look at a different game here. And so I'm going to talk about something called the White Hoff game. All right. So all right. So the White Hoff game. All right, so there are 2 ways to phrase this. The more fun way is to think about this as a chess piece, playing things on the chessboard. So you would imagine you have You have a chessboard kind of, and what you have here is a queen, right? So essentially you have a queen. Right? So how do you draw a queen? This is apparently how you draw a queen. That's terrible queen. Okay, never mind. Okay, never mind. That's fine. So imagine that this is a queen piece, and you have these lines. You imagine this is a chessboard. So you have these lines going through here like that. Okay, I'm gonna erase this. Okay. Okay. And the idea of the queen is that it can move in any of the 8 directions possible in chess. But in this case, we're going to limit the movement of the queen to moving to the left, moving down, or moving diagonally to the southwest. Okay, so moving diagonally to the southwest. I'm going to label the boards like this: 1, 2, 3, 4, 5, 0, 1, 2, 5. So imagine that this is a chessboard. This is a 6x6 chessboard. Position of the queen is at 5, 5, and can move in these 3 directions. Okay, right. So it could, for example, move from this, which is 5, 5. It could move to this is one option. One option is 5, 2. Move there. It could also move here, which is 0, 5. Or it could move to here, which is 2, 2. Right? So there are other ways you can move the queen. Right? So that is the White-Hoff game. Okay. And you cannot move beyond the 0, 0 square. So the 0, 0 square is where things end. Okay, so this is a death trap. Okay, so your game loses if this comes to the queen, right? So this is the losing game. And so when the queen hits that spot, then it is game over for whoever gets the queen at that spot. Okay. All right. So that is the game. Okay. All right. Now, another way to think about this game is to say that essentially you're keeping track of 2 numbers, one on the x direction, one on the y direction. You're keeping track of 2 positive numbers or 2 non-negative numbers. And each time you're either moving left, meaning you're reducing the x number. You're moving down, meaning you're removing the second number. You're reducing the second number. Or you're going diagonally, so you're moving the same number from both. So from 5, 5 to 2, 2, you're removing 3 from both. Okay. So you can also think of this as a nim game with 2 piles, where the available moves are. The available moves are removing chips from one pile, or removing the same number of chips on both piles. Okay, so this game here is like a nim game with 2 piles, and the available moves are you can remove chips from the first pile, removing chips from the second pile, or removing the same number of chips on both piles. And that is the White-Hoff game. Okay. Any questions so far? Okay. All right. So we're going to try to find some nimbers for this game. Okay, so some nimbers. Okay, and I guess I should copy. Well, let's just redraw this. 1, 2, 3, 4, 5, 6. It's not. They don't think I'm drawing a straight line. That's the problem. No, still not a straight line. Oh, whatever, this is fine. Now it's a straight line. Okay. All right. Okay, so let's find some numbers. All right, so you have well, we have 36 spots. First of all, you should note that this is symmetric. Right, so this is symmetric, so it is symmetric across the diagonal because there is really no difference between either pile. Right, so you're going to see a symmetric along this line here. Right, so this will be equal to this one, and this one will be equal to that one. Okay. All right. So we'll start with the easy one, which is start 0 here at the very beginning. Right? So start 0. That is the losing position. Once the queen is there, you cannot move. So that's a losing game. Okay. Okay. All right. So now we're going to do the next one, which is the one next to it. Does that show? I guess it doesn't show up really nicely. And so if I do this one here, well, if the queen is there, there is only one option, and that is the one that starts 0. Right? So in this case, it will just be the max of stars, the max of 0, and that's just going to be 1. Okay. And then you can see the next one here at 2, 0. The options are star 0 and star 1. So the options are equivalent to star 0 and star 1. So the max of 0 and 1 is just 2. So that's why you have star 2 here. All right. And you can probably tell where this is going. So this is going to be star 3, star 4, star 5, etc. Okay. And because it's symmetric, I can go up like this. Star 5. Okay. Okay. All right. Okay, so let's look at other squares. Other squares are slightly more complicated. Okay, so let's see if you look at this square here. Okay, so if the queen is at that square, then you are going to have a few options here. So the queen can move to the left to get this. It can move down to get this, or it can move diagonally to get this. Right, so that is 0 and 1 are the options. Oh no, what happened? 0 and 1 are the options. So the max of that is just star 2. Okay. All right. Okay, so that's probably not that exciting. So maybe I'll look at this one. Okay. So in this case, we can move to either star 1, star 2, star 2 here, or diagonally to star 1. Right? So these are the 4 options of this square. Right? So the options are star 1 and star 2. And the max of this is actually star 0, because 0 is not in this set of numbers. So it is star 0, and this is actually a losing game. Okay, so this is a losing game. All right. Okay, so I'll do the rest of them fairly quickly, and I'll probably make a mistake, but you can probably let me know if I make a mistake. From here is 0, 1, 2, 3, and 2. So this is going to be star 4. Yes, okay. And this one is going to be 0, 1, 2, 4, and 3. So 0, 1, 2, 3. So that one is going to be star 5. Just want to make sure I'm not doing something stupid. Yeah, that's fine. All right. Is this one more interesting? This one is more interesting, I suppose. This one has 1, 2, 0, 4, 5, 5, and 4. And so 1, 2, 0, 4, 5, 5, and 4. Hopefully you can figure it out now. So we're missing the 3. So this one's actually star 3. So it's not what you expect there. It might not be what you expect there. All right. All right, so with that, I will fill out the symmetric by symmetric thing. It goes like this. Okay, I will just do one more row and that's it. Okay, so for 2, 2, for this one, you had 2, 0, 2, 0, 2, 0. So that's going to be start 1. For the square, 0, 1, 2, 0, 1, 3, 4. 0, 1, 2, 3, 4. So that's going to be start 5. For this one, 2, 0, 1, 5, 4, 2, 4, 5. I don't have the 3, right? I don't have the 3. Yes, okay, I don't have the 3. So that's a 3. And the last one, 2, 0, 1, 5, 3, 5, 3, 5, 3. I think I don't have the 4. So that's going to be a 4. All right. 5, 3, 4, etc., etc. Right, so these are the nimbers of these spots for the Whitehoff game. Okay. All right, good. Any questions so far? Okay. Right. So if I want to find a winning move, so for example, if I want to find a winning move from 5, 2, for example, where is that? That is here. Okay. So you look at its options, or you look at its options, which are 2, 0, 1, 5, 3, 5, 3, 5, 3. There is a 0 in there. Right. So this is the 0. So we will be moving towards that. Okay, so the option, one option, which is 1, 2, is start 0. So we move to, yeah, 2, 1, 2. So basically removing 3 from the first pile. Okay. Are there any patterns for this game? Well, that is an interesting question, and I'll show you one result of this game soon. Okay. All right. So if you want to combine this game with other games, for example, if you want to combine this with a NIM game, then you would be doing something similar, except you'll be moving towards some option that is corresponds to a winning NIM game. Right, so say I have, as I say, 5, 2 in the Whitehoff game. And let's add the star. This is star 4. Is there anything that will make it more interesting? Let's say star 3 NIM game. Right, so let's say this is, so we want to have, so let's add these two games together. Right, so what we have here is star 4 plus star 3. Star 4 is 1, 0, 0, star 3 is 0, 1, 1. So the result is 1, 1, 1. So that is going to be star 7. Star 7. Okay. 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 All right. So star 7, and because the first one is the one that is the leading term, that's 1. So it deals with the star 4. So we want to move the so move this. Oops. Move the star 4 to a star 3. we want to move *4 to a *3. So in this case, we can either move here, or move here. Right, so we can either move to 4 2 3 0, yeah, or 5 1. Okay. All right. Even removing 4 chips from the first pile. Yes, it is. Okay, thank you. So that's 4. Thank you. Yes. I think as you will see as we go along this course, I'm very bad at arithmetic. So oh, somebody went out when I said I'm bad at arithmetic. I'm sorry. So anyway, any questions so far? Okay. So I have made a screenshot of what some of the nimbers look like for this game, and this is what it looks like. So essentially, there is not much pattern in this game. There is not much of a pattern in this game. Okay. So essentially, because there's no pattern in this game, that means that if you want to find a number for a particular entry, you would need to look at the numbers of all the options. So that means that for each of these options, you need to figure out the numbers for those options, etc., etc. Okay, so when you do that, that is kind of a lot of work, essentially, right? So this is not exactly a game that you can solve quickly. Okay, all right. But I will show you something quite interesting, possibly. Okay, and that is I want to highlight the places where it is a losing game. All right, so let's look at where the losing games are. It's at the start. It's here, 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 here. Okay, it's symmetric as you would expect. It is what we expect for a White-Hoff game. Okay. But you might also notice that they kind of form a line. Right? So they kind of form this line here. Right? So they kind of form this line. So all the zeros seems to be on that line. Okay. All right. So, so there is a result that I want to talk about. I won't prove it because I don't know how to prove this. But this is a result from White-Hoff. I guess that's why it's named after him. Okay. So the losing games of the White-Hoff games are of the form, and this is, I need to copy this down very carefully. You can enumerate all possible losing games in this game. And that is, let's write down coordinates, the floor of 5n and 5 square n, and symmetrically 5 square n, 5n, for n going from 0, 1, 2, etc. Okay. And then you say, what is phi? Well, phi is that famous number that is 1 plus root 5 over 2, and that is the golden ratio. Okay, so you have seen the golden ratio before, hopefully. All right. So this comes out of the Fibonacci number, essentially, and in fact, there is a relation between the numbers of this game and the Fibonacci number. Okay. Right. So in fact, what we have here is that this line here, I guess this line here, represents the things from. I guess I really ruined this picture, didn't I? Okay, so let's say this line here, it represents the coordinates from the first set, right? So the slope of this line, is just the golden ratio. Okay, so it is the golden ratio. So that's phi squared divided by phi. Okay. And the other line here, here we go. The slope of the line is 1 over the golden ratio. Okay. Okay, so that is a nice result that is in this game. I don't know how to prove it, but it is a fairly strange result, but also quite interesting. Okay. Anyway, so that is the Whitehoff game. All right. Good. All right. Any questions you have about the impartial games things? All right. Okay. Any questions about other things? I guess we have the lectures have moved on from impartial games to the strategic games. It's strategic is one of those words I can't say, so that's very unfortunate. But yeah, so it is about Nash equilibrium and stuff like that. How did you find the first week of stuff? And do you have any questions about those materials?
I had a kind of specific question about one of the exercises from the lectures.
Okay, sure.
It was the example about the guessing 2/3 average game.
Oh, that one, yeah.
There was, I'm not sure if like this is an assignment question that I can ask, but if it's not, then I was confused about exercise 10.1 about proving that 111 is the only Nash equilibrium of the game. Like, I don't see that at all.
Okay, so the story of this exercise is that I gave this as an assignment last time, and it was a disaster because it is a lot of algebra, right? So the idea of proving that 111 is the only Nash equilibrium is to say, suppose I move. So you have to prove that it's a natural equilibrium. So you say, suppose I move from 111. No, proving that it's a natural equilibrium is easy, but proving that it's the only natural equilibrium is the hard part, right? Because you need to say, given any 3 possible strategies that are played by the players, you have to prove that there must be a way to improve it. And it often involves looking at some of the fractional stuff. Let me look at my thing and see if I have a solution for this one. Yeah, it's very ugly. Yeah, so yeah, you had 2 cases where Yeah, it's basically saying, so yeah, the proof is going to be something like playing a number is no better than playing one less of that number. And yeah, my proof contains so many fractions that's not worth doing for you. So I'm not going to, so first of all, I'm not going to make that an assignment question, but at the same time, I would not spend too much time trying to solve this exercise either. I think the main point about this exercise is trying to know, figure out how to prove that it is the only Nash equilibrium, I guess, in general, or the strategies for proving that. Yeah, so that's my answer to that question.
Thanks. But is there a way to like intuitively see why that would be the case?
Intuitively, it is if you play a number and you already get a utility of, say, you share 3 ways or 2 ways or 1 way. Well, actually, yeah, you share that. You would, when you, the intuition is, if you drop your number by 1, the average is not going to drop by, the average should drop by 1/3, essentially. Yeah. But yeah, that caused all sorts of troubles for me when I tried to prove this. Yeah.
Okay, thank you.
All right, no problem. All right, okay. Are there other things you would like to ask about? Hopefully the strategic game stuff is not too difficult for now. It will get slightly harder when we start doing the mixed strategies where you have probabilities involved. And also, I guess this is a good time to remind you to review linear programming a little bit, because that will come up in next week's lectures. Is it next week? It could be after reading week. Actually, I'm not sure. Maybe review the review some linear programming in during reading week. Reading week is coming soon, so that's also nice.
There's a question in the chat.
Sorry? Question in the chat. Can you elaborate on that game? I don't know. There's not much to elaborate on that game. Let me bring up the game. I guess I have to. Here. Yeah, so for this game, it's just trying to find the best response function, given how you play each one, each strategy. So we can go over the first one. For example, this one is the best response function for the player 1 if the player 2 plays X. Okay, right, so player 2 plays X, so this is what happens here. Player 2 plays X. Okay, so then we look at what is the utilities for player 1 given that player 2 plays X. Okay, right, so if player 1 plays A, it gets 1. If player 1 plays B, it gets 2. If player 1 plays C, it gets 0. Okay, so it gets 0. Okay, so the best response here is the second one, right? 2 is the highest number here, so that is in the best response. Okay, so that's why we include only B in the best response function, and that's why we put a star around the 2. Okay, all right. And if I say, let's look at this one when, so this is when player 1 plays B, what happens to player 2? Right, so what are the possible best responses from player 2? Okay, so when player 1 plays B and player 2 plays X, it gets 1. When it plays Y, it gets 1. When it plays Z, it gets 0. Okay. Right. So the best response here would be the 1. The 1 is the largest number. Okay, so that's why you will have X and Y, both of these, in the best response for player 2. And so given that player 1 plays B, player 2 would be able to choose either X or Y. Okay, all right. Okay, all right, so once you have calculated the best response for every possible solution, every possible strategy here, you're looking for the overall strategy, the strategy profile, where both players are playing their best response. Right? So in this case, the 2-1 here that we just described, playing. So player 1 playing B means that X is the best response, and player 2 playing X means that player 1 playing B is the best response. So they are best responses to each other. So that means there is no reason to actually deviate from this choice. And player 2 could change to Y if they want, but they don't get any benefit from their utility. And they certainly don't want to change to Z, where the utility goes down. Okay. And for player 1, if they change to A, it goes down, change to C, it goes down. Okay. So that's why this is a Nash equilibrium. So there's no reason for any of the 2 players to change their strategies if both of them, if player 1 plays B and player 2 plays X. Okay. And here is another one that is in common for both of them, and that is another Nash equilibrium. Okay. All right, so that's how you do these calculations. Is that good? Any questions about this? In the real case, which strategy will they play? Well, we don't know, right? So we don't know. So you'll see in this week's lectures, we'll talk about dominant strategies, right? So strong dominance and weak dominance. If it's a strongly dominant strategies, then they will definitely play that. But in general, when you have Nash equilibrium, all we know is that if they play this, it's going to be quite stable. They're not going to change, right? But but as to which ones they are going to actually play, we don't know. Maybe they will have to. So there are other theories behind how Nash equilibrium works that discusses this. But either one, either this strategy or this strategy will work for a Nash equilibrium, but we don't know which one they will play. There are some theories about if they play this multiple times, then they will settle on the one that is they both like, or you just settle on one of those 2. Yeah. Will it end up with BZ? No, they will not end up with BZ. Right? So both of them get 0. Okay. Yeah, both of them get 0, so they could always improve on that. So they will never end up with BZ. Yeah. So it will always be either bx or cz. All right. Okay. All right. Any other questions? Oh, we actually have only 2 minutes left. Wow. Okay. I did stretch it out quite a bit today. Okay, that's good. Okay, if there are no other questions, then I'll say thank you very much for coming. Have a good rest of the day and the rest of the week. Won't see you again. I won't see you next week, but because of the quiz. But hopefully you can come during the office hours and we can talk about things if you want. But otherwise, hopefully you have a great week. All right. Oh, I should stop
you.
this recording. Okay.